Okay, so welcome back. Let us talk about a little more about this lift and drag force, which we talked about previously. So both lift and drag force depend on various geometrical parameters and angles of drag. As you have seen in the wing geometry, there are many things as the camber of the airfoil or the aspect ratio of the airfoil. So many things are there, many geometrical parameters are there which influence this lift and drag force, and also the angle of attack is also there. So to reduce complexity, we club all this term into one single non-dimensional term. We cannot worry about all these things at once, so we try to club this thing into one single non-dimensional term, so that we don't have to worry about each single term separately. So these non-dimensional terms, these are called as the lift and the drag coefficient. Very important. This is represented as CL and CD. These are lift and drag coefficient, and the lift and drag force are given by this formula. The force of lift, this is stated as half rho v square. This is the density, this is the velocity, this is the drag coefficient, and this is the area, the planform area, which we have shown as the hashed section, if you remember. Also, the drag force is similar. It's half rho v square CD times S. This is the lift coefficient. This is the drag coefficient. And if you remember this is nothing but your dynamic pressure, which you studied in the Bernoulli's equation. This is the dynamic pressure. This is how lift and drag forces are calculated. Okay, so this, as we have talked about the non-dimensional term, the lift coefficient and drag coefficient, they depend upon the angle of attack, alpha. The angle of attack, see, this is the angle of attack, it's changing the angle of attack, and with this change in angle of attack, the lift and drag coefficient are also changed. What happens with coefficient of lift is that as the angle of attack increases to a certain degree, it increases. As angle of attack increases, this lift coefficient increases. As it is turning upside up, the angle increases, alpha increases, so lift also increases. But what happens after certain time is that there is a very high wake created, or the pressure, the air separate. If we keep the angle too high, so what happens is that in that condition there is a sudden decrease in lift and very high drag is produced. So at that condition is called a stall of the airfoil or stall of the wing, and the angle at which that happened is called stall angle, where there is a sudden decrease in lift. See, the lift increases, the alpha increases, but at this point there is a sudden drop in the lift. It's called stall angle. Okay, and this is the drag coefficient, how this varies. So as you've seen, that drag coefficient is a sum of two types of drag. This is the CDO. This is called as a parasitic drag. Parasitic drag, nothing much, the skin friction drag and pressure drag, which you talked about. This is not dependent upon lift, and hence it also does not depend upon alpha. As you see that this is CD, it does not changes with alpha, it remains same. So this component does not change with lift, but this is the induced drag coefficient, and this changes with lift. And here's the formula about this. This is the lift coefficient. See, the drag coefficient is directly depending upon the lift coefficient. Very important. This is pi, and this is the span efficiency factor. For our purposes, we will take this at 1 as 1, and this is the aspect ratio. If you remember, span upon area. In previous lectures, I told you about the aspect ratio. This represents the slenderness of the wing. Okay, so this we will talk about in the next slide.